Okay, let's get started. Thank you for joining today's talk by Jeff Dean. So it's a great honor and pleasure to have him here in Korea for this talk. So yeah, nice to meet you. My name is Sun Sun from Google's developer relations team, and we will have one session by him, and then we'll followed by Q&A. So I don't think he needs much introduction. So why don't we just get started with his talk. Please welcome Jeff.
Okay. All right. So thank you very much for coming. What I'm going to talk to you today about is sort of the work we've been doing over the last 5 or so years at Google on using deep neural nets in various ways in our products, sort of on the research side, on the computer systems side, and then working with lots of product groups on how to sort of use these kinds of technologies in ways that improve our products for users. So I'm going to be presenting work that is not just my own, but is often work done by many, many, many other people. So this is not just me. This is like a very big effort at Google. You'll see some things with lots of names on them, and it's indicative of how much effort there is across Google in this area. So one of the things I really like about Google is our goal, which is nice and broad, and it really speaks to understanding information is kind of a very key part of that. If you can't understand what's in information, it's going to be very difficult to actually organize it. And so what do I mean by that? It's really, really hard to do this without understanding. And we're not really there in terms of understanding. We've made pretty good progress in the last 5 years. So let's look at a few examples. So if I showed you that picture, you'd have no problem writing, a sentence about that picture. You could tell me a caption says, it's a cute young girl, she's holding a teddy bear. And traditionally, computers really have been pretty bad at understanding kind of visual and perceptual kinds of information until fairly recently. If you have a street scene like that, you have no problem picking out the text in that street scene and understanding that store sells souvenirs and they have really low prices because they would never lie to you. If you really want to understand the world, the physical world, and you have imagery like this, a computer needs to be able to pick out what are the interesting bits of information there and read the text and understand it. The majority of computer interaction today and going forward is going to be by small mobile devices. And that really means that you need different kinds of user interfaces for those devices. You need to be able to really understand speech, to generate speech effectively, to really have a form factor that works for people. And so having really, really good speech recognition is another key thing. If you're talking to another person, there's no question they're going to understand you. Whereas when you speak to a computer, it's often not the case that the speech recognition is as good as you'd like it to be. Even something as simple as seemingly simple as search, if I have this query, car parts for sale, if you just go by kind of superficial characteristics of documents, that first document is going to look like a better match because, well, it has lots of red words in it that match the query. But we all know that the second document is much more relevant to that query than the first. So really understanding what that first query means at a deep level, not just the superficial kind of individual word level, is what you really need to build good search and good language understanding products. Okay, so first, how many of you are familiar with what a deep neural net is? Okay, some of you, not all. So I'm going to have a bit of an overview about what deep neural nets actually are, and then I'll talk about 2 main areas that we've been applying deep neural nets, the kinds of perceptual problems like vision and speech, and then I'll talk about some language understanding kinds of applications. And then I'll tell you about TensorFlow, which is kind of the second version of this of software that we've built for really training and using neural networks in various products. So the project that I'm working on now started about 5 years ago, and our focus initially was on really pushing the state of the art in what we could do with neural networks. Neural networks have been around for a really long time. They've been, at least in computer time, they were invented in the 60s and 70s, and were initially popular in the late 80s and early 90s. And then they kind of faded away because although they could be shown to do really interesting things on kind of small problems, we really just fundamentally lacked two things. We lacked enough computational power to train very large models on sort of really large and interesting data sets, and we also kind of lacked really big, interesting data sets at that time for which they would be really, really useful. So we started the project in 2011, kind of trying to reinvigorate pushing the boundaries of large-scale systems for neural nets. So this is about when we started the project, and we started working with just a few product groups at Google and also doing research on our own in this domain in 2011 and 12. And over time, what we've found is that as we worked with a few other product groups and they released something that was good and they solved some problem they previously weren't able to do, word got around, and then some other teams would come talk to us and they would say, hey, we have this other problem. We think it's kind of similar. And over time, there's been a pretty dramatic increase as more and more teams have discovered that, hey, we can use this for our thing. And I think it's kind of nice to see the breadth of different areas that you can apply these kinds of techniques to. Everything from drug discovery to image understanding to, robotics and speech and translation. And the reason for that breadth is really you have these same fundamental building blocks that you can apply in lots of different areas. You sort of can feed in one kind of information, decide what kind of information you want to get out, collect together some training data set that is indicative of the function you want to compute, and off you go. And you can kind of mix and match these different areas, which I think is part of the power of why these models work so well. You feed in very raw forms of data. You don't have to sort of hand engineer lots of interesting features. The power of the model is able to derive what's interesting about that data set automatically from just observing lots and lots of examples. And so you learn these common representations, potentially even across domains, so that the word car can mean the same thing as an image of a car in some cases if you train different models correctly. We've often seen that we can also take a whole bunch of subsystems, that some of which may be machine learned and some of which may not be, and replace that with a much more general end-to-end learned machine learning piece. And that's really nice, because often when you have lots of complicated subsystems, there's a lot of complicated code to kind of stitch them all together into a real final system. And it's nice if you can replace that with data and very simple algorithms. So what do neural nets do? This is a bit of background for some people. Essentially, they learn a really complicated function from data. That's their main essence. And so they allow you to transform inputs that are in one space into outputs in another space. Now, these inputs, this function is not like x squared. It's a really complicated function. In particular, you can feed in things like raw pixels and have the output be a prediction of which one of 1,000 different classes of categories of object is that in that image. And it's essentially, when you hear the term deep learning, just think of a large, deep neural net. Deep refers to the number of layers, typically. And so this is kind of the popular term that's been adopted in the press. But I think of them as deep neural networks, generally. So one of the nice properties this depth has is that the system is composed of a collection of simple and trainable mathematical functions. And I'll show you in a minute what that's like. It's compatible with a lot of different variations of machine learning styles. So in this case, where you have an input like that image and then an output where you've got a human to label that image saying that's a cat, that's called supervised learning. So you essentially can give lots of supervised examples to this system, and you're going to learn to approximate a function that's similar to the one it observes in those supervised examples. You can also do unsupervised training where you're only given images and you don't know what's in them. And the system can then learn to pick up on patterns that occur across lots of images. So even if I don't necessarily know what to call that, I can recognize that there's something in common about all these images that have a cat in them, even if I don't know what to call it. And it's also compatible with more exotic techniques like reinforcement learning. Reinforcement learning is a very important thing that's being used as one piece of the AlphaGo system that will be on demonstration on later this week. Okay, so these models are kind of loosely inspired by how we know real brains behave. And I say only loosely because we're kind of treating them at the level of, well, we know there are neurons and they're connected together. And when neurons take inputs, they sometimes produce an output. It's not simulating things at the very deep chemical level where you're trying to understand exactly how neurotransmitters cause this neuron to generate output. Rather, it's this very simple kind of abstract notion of a neuron, where a neuron has a bunch of inputs at the bottom there. We know that real neurons can associate different strengths with different ones of its inputs. So what we're trying to do in an artificial neural network is to learn weights on all those edges that are the strengths that we associate with the different inputs. And we know that real neurons essentially take in some combination of their inputs and the strengths, and then they decide to either fire or not, typically. They either spike or not. In our artificial neurons, instead of just this binary spike, we're actually going to emit a real numbered value. And so the function these neurons compute is the weighted sum of their inputs times the weights applied through some nonlinear function. And typically, the nonlinear function we're using today is called a rectified linear unit. It's the max of 0, x. This is sort of the world's simplest nonlinear function. In kind of the 90s, a lot of these nonlinear functions were much smoother mathematical things like sigmoids or tanh functions. But now we're kind of using this. This has the nice property that it actually gives you true zeros when the neuron doesn't fire, as opposed to a value that's very close to 0. And that can sometimes help you when you're optimizing the system. So to make this even more concrete, the weights are just floating point values. And then there's kind of how this particular neuron would generate its output from the inputs. So we're going to go through these nice layers. We're going to, some of the neurons will fire or not based on their inputs. The lowest level neurons will look at little patches of pixels in this case. The higher level neurons will look at the outputs of the neurons below and decide to fire or not. And we'll work our way up and we'll say, the model predicts that's a cat. Oh, well, that's wrong. It's a dog. So at that point, we'll actually get a signal that we should have said something different. And we can make adjustments to the rest of the model so that we make it more likely that we're going to say dog when we see this image next time rather than cat. And that's the whole goal of training a neural net, is to make little adjustments to the weights on all the edges throughout the model to make it more likely that you get that example right. And then you kind of try to do this in aggregate across all the examples so that in aggregate you get most of the examples right, or ideally all of them, but typically not quite all. The learning algorithm is actually really simple. It's this loop. So while you're not done, you're going to pick a random training example. This is for supervised training, so I have the input, and then I have the desired output, the label. I'm going to run the network on input and see what it produces. So I propagate forward, run all those neurons, and then I'm going to adjust the weights on the edges in the process I'll describe to make the output closer to label. And it turns out that good old Newton has solved this problem for us. We can actually use calculus and the chain rule to determine at the top when I said cat instead of dog, I can understand how I should adjust my weights at the top layer to make it more likely that I'm going to say cat. And essentially, if this is, or say dog. So if this is dog, and I'm currently saying this, I can understand that I need to go in this direction with the weights to get it so it's more likely to say dog. Now I don't want to take a big step because this is a very complicated, uneven surface. So I'm going to take a very small step to make it more likely that I'll say dog next time. So I'm going to take a little step maybe to here. And through lots of iteration and lots of looking at the examples, I'm going to essentially make it more likely that next time I will say dog and say all the other image labels correctly. And then through the chain rule, I can understand how changes in the parameters in the lower layers will affect that output. And that's pretty important so that I can ripple the changes that I want to make to the network all the way through, back all the way to the input, and make the whole model adapt a bit to be more likely to say dog. So in very simple terms, that looks like this. We're going to adjust some of the parameters. We're going to make little teeny adjustments to them. And then next time, the output of the neuron will be a little bit different. So the whole model will compute a slightly different function. Now, in actual fact, this is a pretty complicated 2D function, 3D function. But real neural nets are composed of hundreds of millions of parameters. So you're making adjustments in this 100 million dimensional space and trying to understand how that affects the output of the network. So another nice property of neural nets that I was relaying is that you can apply them to lots of different kinds of problems. And you have lots of real interesting data in the world that you might want to be able to understand. So there's lots of text, there's trillions of words of English and lots of other languages. There's lots of aligned text where you have translated versions of one language and another, sentence by sentence level. There's lots of images and videos, plenty of audio, lots of user activity in using lots of different kinds of applications or using search engines or using people sending emails, marking messages as spam. There's lots of activity that you can learn from and build intelligent systems. Another nice property of neural nets is the results tend to get better if you throw more data at the problem and you also make your model bigger. If you throw more data at the problem and you don't make your model bigger, at some point the model's capacity is saturated with learning the kind of more obvious facts about your data set. And what you really need to do when you increase the size of the data is to increase the size of the model so now the model can remember not just the obvious things but the very subtle kinds of patterns that occur maybe only in a tiny fraction of the examples in the data set you're giving it. The unfortunate thing is to do larger models on more data, you actually need a lot more computation. So a lot of what we've been working on is how can we scale the amount of computation we need to throw at these problems in order to train bigger models on more data. Along the way, people have also been developing better algorithms and new insights into what kinds of models are particularly effective for different kinds of problems is also useful. Okay, so let me talk about a few different kinds of places we've found that are pretty amenable to using deep learning in product ways. So one is in speech recognition. This was one of the first teams that we worked with to deploy neural nets, and we initially helped them deploy a new acoustic model that was based on neural nets instead of the hidden Markov model they were using. And the problem of the acoustic model is to go from 150 milliseconds of speech to predicting what sound is being uttered in that middle 10 milliseconds. You know, is it a b or a f or a k? It sounds good with the mic. And essentially then you have a whole sequence of these predictions and then you stitch that together with a language model so that you can understand the user said, how cold is it outside? And the initial thing that we helped launch reduce word error rates in the speech recognition system by more than 30%, which is a really big deal. Some people who've been involved in speech research for 20 years said this was the biggest single change they'd ever seen, biggest single improvement. And since then, they've been working in the speech team on using more and more complicated and advanced kinds of networks to models to further reduce the error rate. And they've been making a lot of progress in this general area. So generally now when you speak to your phone, it's much better than it was 3 or 4 or 5 years ago. Okay. So one of the really interesting things that happened about 5 or 6 years ago is the release of the ImageNet dataset. So the ImageNet dataset is sort of one of the biggest at that time datasets for computer vision. It was about 1 million images with 1,000 different categories, and you had 1,000 examples of each category. So you have 1,000 different pictures of leopards that you can train your models on, 1,000 different pictures of motor scooters, and then the goal is to generalize to new kinds of images. Can you say, for a new image, that's a leopard, or that's a cherry, or a mushroom, or a car? This was much bigger than most of the data sets computer vision researchers have been working on at that time. And it's really kind of, the release of this data set has really pushed the field of computer vision forward a lot, I think. So typically these models, you get the true label in the training data, and then the model outputs a probability distribution over the 1,000 classes. And so for some kinds of objects, it's very confident that this is a leopard. So you see that the first prediction is correct, it's red, and it's very confident in that. Whereas for some of these, it's not quite so sure, and it actually never did get that that's a Madagascar cat. Although it looks like a lemur to me, I don't know. Yeah. With 1 million images, not all the labels are correct, which is another problem with machine learning. So over time, people have been developing more and more complicated and sort of powerful models for doing computer vision, and particularly in the context of the ImageNet challenge. I think that's been a really nice thing to push the community forward. So this is a team at Google, including some people in our team, as well as people in the perception research team, developed this kind of complicated model where each one of these is kind of a whole layer of neurons that is doing different kinds of convolutional operations. And it's a pretty big and deep model, and it's pretty accurate. So here's a chart that illustrates how much computer vision has improved on this ImageNet challenge. So before people started using neural nets, they had the challenge only for a couple of years. And the error rates in the top 5, where you get it correct if any of your top 5 predictions are the correct label, and you get it wrong otherwise. So the error rates were something like 25, 26% for not getting it correct in the top 5. And then the next year, Alex Krizhevsky, Ilya Sutskever, and Geoffrey Hinton entered the challenge with a neural net, and no one else at that time was using a neural net for this task. There were a lot of scaling challenges in getting that to work. And they did way better. I think the second place team was roughly around that error level. And so people saw this very dramatic jump in performance at that time. The next year, Clarify, which was started by my former summer intern, Matt Zieler, he won. Yay, Matt. Good job. The next year, the model I showed you, the complicated one developed by a team at Google, won. And one of the interesting things that happened that year was Andrei Karpathy is one of the Stanford grad students who helped administer the contest. And they were sitting around at a group meeting apparently, and they said, "Oh, I wonder what humans can do on this task." And so they sat down in their group meeting and they tried to label some images. So they were looking at these images and saying, is that a Madagascar cat? And they're like, I don't know, this is hard. So he decided he would go home and actually train himself over the weekend to label ImageNet images. He has a great blog post about this, so you should look it up. It's kind of fun. So he did the right machine learning thing. He separated he had a set of training images and then a bunch of test images he'd never seen before. And he sat down for 100 hours and looked at the training images. And he got 5.1% when he got to look at the test images. This is actually a pretty hard thing. You can try it yourself on ImageNet images. He also convinced one of his lab mates to do it, but they only did 12 hours of training instead of 100, and they got 12% error. So not so good. So it's a pretty hard task. And since then, computers have continued to improve in their ability to do really good image recognition, at least on the ImageNet challenge. And that's, so you see 25% error down to 3-ish% error in 5 years is pretty good. And these models really work. They're very, very strong at doing very fine-grained distinctions. They're actually stronger than people. In Andre's blog post, he wrote about an analysis of the kinds of mistakes the computers made and the kind of mistakes he made. And he was terrible at distinguishing the 40 breeds of dogs in the ImageNet challenge. But computers are actually pretty good at that. So they, I would say flower, but the computer model can do a much better job than that. It can say hibiscus, dahlia. It's very good at generalizing to different kinds of images that all have the same label. So these images visually don't look that similar, but they're both labeled as meal. When it makes a mistake, it's sort of understandable why it makes that mistake. It's not a snake, but you can understand why it might have said that. I know that's not a dog, but I'm actually not sure what that is. So that's sort of hard. I know the back one's a donkey, and I think the front one is either a donkey or a goat. What do you think? Goat, you think? Yeah. Probably. It's unclear. Anyway, so that ability to look at pixels and then understand what's in the image is a pretty powerful one. And the Google Photos team rolled out the ability to search all your photos without tagging them. 3 or 4 years ago, when you wanted to search your photos, you had to tag them, and you'd say the person's name, or you'd say beach or things like that, and then you could find your pictures of the beach. Now you don't have to do that. So this launched first in Google Plus photo search, and so here's a happy user. They're like, wow, that's a bit insane. I didn't tag those. So he could find his pictures of statues. Or see, here's another happy user. I just typed drawing and I found all my scribbles at once. And I'm pretty happy we got the Yoda picture correct, because this is a slightly unusual looking Yoda. We also have a lot of much finer, sort of more specific kinds of visual tasks. So in Street View imagery, you want to be able to read all the text. And one of the first things you need to be able to do is find text. So my summer intern, Matt, worked with the Street View team to train a model to essentially predict a heat map of pixels, like which pixels contain text and which ones don't. And the training data was just sort of polygons drawn around sort of pieces of text. And because the training data included different kinds of character sets, it has no problem finding text of all kinds of characters. It works with big fonts and small fonts and words that are close to the camera and words that are far away in different colors. And that's, a relatively easy model to train. It's just kind of a convolutional network, and you just try to predict per pixel, does that contain text or not? We've also been working a lot with the search ranking team on releasing a neural net as one of the signals in search ranking. So one of the things about search ranking is they tend to want to have a model that is very understandable, so they understand when it's making certain decisions. And that was kind of one of their initial hesitancies in using a neural net for search ranking. But we helped work with them to build enough debugging tools and understandability into the models that they became comfortable with this. And now when we launched this, it's now the third most important search ranking signal, which It's pretty good. I don't know. It's good. So another interesting kind of problem is this model developed by Ilya Sutskever, Oriol Vinyals, and Kwok Lee in our group, which was essentially they looked at this problem and they said, a lot of problems in the world you can frame as mapping one sequence to another. And in particular, they looked at the problem of language translation and said, well, that's really just mapping a sequence of English words into a sequence of French words, or vice versa. And so one of the, neural nets are really good at learning very complicated functions. And so the function of English to French sentences is actually the function this model learns. And so you essentially just input, a sentence in one language, one word at a time, and then you get this end of sentence signal. And now the model is trained when it sees that to start producing the corresponding sentence in the other language. And the training data that it gets is language pairs that mean the same thing, language sentence pairs. And it just tries to model that function. And that's pretty much what it does. And at every step here, it's emitting a probability distribution over all the vocabulary entries in your vocabulary. And so when you're actually doing inference, instead of training, you need to do a little bit of a search, because if you just maximize the probability at each one of these words, you're not necessarily going to get the most probable sentence, which is what you care about. So you can do a little bit of a search over the set of the joint probabilities until you find the maximal probable, or a maximally probable sentence. And that system actually works well. It achieves state-of-the-art on a public translation task. Whereas most other translation systems are, a bunch of kind of hand-coded or machine-learned models for sub-pieces of the problem, rather than this full end-to-end learned system. So that's caused actually a pretty big explosion of lots of interest in this general model, because it turns out a lot of problems can be mapped to that general sequence-to-sequence problem. Here's just a few examples. So one of the things I really like about the machine learning research community at the moment is it just moves really, really fast, right? So people publish a paper and they put it up on arXiv, which is this paper hosting service. And then within a week, lots and lots of research groups around the world have downloaded that paper, read it, dissected it, understood it, implemented some extensions to it. They've published their own extensions to it within the next week on arXiv. And this is all work that is kind of related to the sequence-to-sequence model, which was published in the end of 2014, December 2014. And there's a pretty wide variety of additional work done by lots of labs across the world. It's pretty amazing. It's different than a lot of other parts of computer science where people would submit a paper and then the conference would decide to accept it or not 6 months later, and then it would come out in the conference proceedings 3 months later, and then by then it's a year, and then you're like, oh, that's cool work. I should look at that. And so getting that time down from a year to a week is pretty amazing. Here's an actual product kind of application of the sequence-to-sequence idea. So one of the things you want to be able to do on a phone is respond quickly to email, right? And it's kind of a pain to type. So in working with the Gmail team, we helped develop a system that allows you to predict what are likely replies for a message. So the first thing we did was train a very small model that says, do I think this message is the kind of thing I would have a very small short reply to? And if so, then we activate a bigger, more computationally expensive model that essentially just takes that in as a sequence and tries to predict the sequence of the response words. And so here you see this is actually one of my teammates who worked on the problem. He got a message from his brother saying, hey, we wanted to invite you for an early Thanksgiving, which is like a big American feast holiday, beginning around 2. Please bring your favorite dish, RSVP by next week. RSVP means tell us if you can come. And so the three replies the model predicted are count us in, we'll be there, or sorry, we won't be able to make it. And that's great. Now you can respond to emails. Actually, a pretty surprising number of Gmail responses in the Inbox app are now generated with this smart reply thing. People seem to really like it. So one of the follow-on bits of work for the sequence-to-sequence work was doing image captioning with the same kind of approach. So in translation, you're trying to maximize the probability of the English sentence given the corresponding French sentence. In image captioning, you're trying to maximize the likely caption a user would assign, a human would write about this image, given the pixels of the image. So essentially, you can just take the kind of the image models that were developed and the sequence-to-sequence models that were developed and cut that in half and glue on the image model at the beginning. So now you initialize the state of this decoder that's going to generate the sentence with, instead of reading the English sentence one word at a time, you look at the pixels of the image. And then you initialize the state, and that state kind of comes out of the top of the image model, which has very high-level features that are representative of what is in that image. And then you're going to train it to generate the caption. And so this is a test image that the model hasn't seen before. This is the corresponding human label. The actual data set had 5 sentences written about each image by different people. So there are about, I think, 700,000 total sentences about 100,000 or 200,000 images. So you see that's what the human wrote. And these are 2 different sentences that the model generated for that image. And you see that's pretty good. Here's some more examples. So it doesn't really have kind of human level of understanding. A human would write a more detailed thing about the tennis player. They might say the tennis player is about ready to serve the ball or something. And we say a man holding a tennis racket on a tennis court, which is true, but not particularly insightful. 2 pizzas sitting on top of, it's actually 3 pizzas on 2 pans. We'll give it half credit or something. And when it's wrong, it's kind of funny, you know. If you look at it just right, though, I assure you that's a man, and there's a snowboard that you just can't see. You can combine these kinds of techniques as well. So this is an app that our Translate team put together that uses computer vision and then recognizes text in the viewfinder and then translates that text on the device. So it's all running on the device. And then superimposes the translated text onto the image. It's actually got a font selection problem in there that I didn't realize until a few days ago. So they have to decide what font they're going to render the new text in. Okay, so one of the things we really care about is being able to make progress quickly in these kinds of domains. So we want to be able to really train models quickly, understand what worked well, what didn't, and figure out what the next set of experiments is that we want to run. And there's a very different feel for that cycle if you're in the kind of minutes or hours end of the spectrum than if your experiments take many weeks or months. So we emphasize a lot in our work the ability to go from an idea to turning that around and training a model in kind of minutes or hours. So train in a day what you could do in a GPU card in 6 weeks or something is kind of what we really aim for, because it makes everyone doing this kind of research more productive. So there's a few techniques you can use to train large models quickly. I'll talk about 2 of them, model parallelism and data parallelism. So model parallelism is this idea that a neural net actually has lots of inherent parallelism because we all these different individual neurons that are mostly independent of each other when you're computing them, especially if you have what are called local receptive fields, where a neuron just accepts input from a small number of neurons below it. So you can actually partition that work. So you could put these on different machines or on different GPU cards, and then you can mostly operate relatively independently. Only data that kind of straddles this boundary where the inputs for a neuron come from neurons that are computed on a different device. Do you need to actually arrange any communication? The second thing I'll talk about is data parallelism. So that's the idea of having this set of parameters in the model that you're optimizing not be in one machine, but instead be in this centralized service. And then you can have many different replicas of the model that are going to collaborate to optimize those parameters. And they're going to read different examples. They're going to read different random pieces of data during the training process. And before they do that, each one of these replicas is going to get the current set of parameters in the model. It's going to then read a bit of data, figure out what the gradient should be, figure out what adjustments it wants to make to the parameters, and then send those adjustments back to this centralized set of parameter servers. And then that set of parameter servers will make the adjustments to the parameters. So now we have a new set of parameters there. And before we processed another few examples, we'll get the new set of parameters and do the same thing. And then you can do this across many replicas. So we use some setups of 500 copies of the model across 500 different machines in order to optimize the parameters quickly and to process a lot of data. And you can either do this asynchronously, where every one of these is kind of in its own loop, getting parameters and computing gradients and sending them back without any control or synchronization with the other ones, which has a downside, which means that when the gradient comes back, the parameters may have moved from where you computed the gradient, right? You're computing the gradient with respect to the current, some value of the parameters. And if the parameters have moved, then that gradient may be slightly incorrect. But it turns out that's sort of okay for a lot of kinds of models. And it's a little bit hard to understand in a theoretical analysis, but in practice it actually seems to work for a lot of problems. Up to 50 or 100 replicas you can do just fine with this. Or you can do the whole thing in a synchronized manner, where you just do data parallelism and you have one controller controlling all those replicas. Both of those seem to work. They have different strengths and weaknesses. Okay, so let me tell you a little bit about the motivation for TensorFlow, which is our second generation sort of software system we put together for these kinds of models. So we open sourced TensorFlow last November with a pretty nice flexible license so that people can take advantage of the system we've built and use it for their kinds of problems. The Apache license means you can basically do pretty much what you want with it. We have actually released the initial updates for the distributed implementation last week. Sorry, I forgot to correct the slide. It's a little rough, but it's getting better packaging in the next few weeks. And there's more info on those websites. So one of the things about the initial release that I think people really liked in the external community is the fact that we put together a lot of tutorials that show people how to use TensorFlow to build interesting machine learned models. So for example, there's one here that shows you how to do a kind of computer vision application. There's one here that shows you how to do the language translation model I described. There's another one that shows you how to train embedding vectors for words that have kind of interesting properties. And it kind of explains both how to use TensorFlow to do those things, but also some of the machine learning ideas behind some of those models. So that's been pretty well received. We also wrote a white paper about sort of the systems aspects of what's going on under the covers in TensorFlow. You can see this is not a smallish project. There's actually a lot of people who've contributed to various aspects of this. There's a whole visualization system for TensorFlow. There's the computer systems aspect. There's the machine learning models and tutorials on top of that. You can find the source on GitHub. We released it in November last year, and we were the most forked thing on GitHub last year, which was pretty good, I guess, since we were only out for 2 months of the year. We've continued to push lots of changes to it, so we've had 1,300 commits to it in the last 4 or 5 months, with a whole bunch of contributors, now some external contributors. That's the whole reason for open sourcing this, is to help have a community around this and have people work with us to improve the system and to add new features that they think are important or things like that. So the first system we built was called Disbelief. And it was really good for scalability, so we could train very large models quickly and so on. We had those nice properties. And it was pretty easy to take models that we trained and put them in production because it was kind of oriented towards sort of being very robust and high performance. But it wasn't super flexible for trying lots of different kinds of more exotic models or reinforcement learning models. And so TensorFlow is essentially our take after experience with building the first system. We wanted to keep the kind of nice properties that Disbelief had, but make it easier to express machine learning ideas. So the core of TensorFlow is this graph execution system that I'll describe in a minute. And then there's different front ends for specifying the kinds of graphs you want to compute. So we have C++ and Python front ends. There's already some, I think, pending changes to put a Go front end on this, and we imagine other languages might get added over time. So the computation is a data flow graph, and the things that flow along the edges in this graph are tensors, so n-dimensional arrays. So think of it like a 2D floating point matrix or a 1D integer vector or things like that. And the traditional data flow model is purely functional. We've augmented it so that you can have state in some of the nodes. So bias is there as a variable. We're going to do a bunch of computation and maybe compute some adjustments we'd like to make to the bias node, and then we can have a node here that updates state in the graph. And that's kind of how you typically represent parameters in these machine learned models. We also designed it so that you can distribute the computations. So you might have a device here in green that might be a GPU card, and this might be your main set of CPU cores. And the system will automatically partition the graph around the set of devices you tell it you have. So you might have 8 GPU cards in your machine plus a CPU, or you might have a distributed system with 10 machines each for the GPU card. And the system accepts hints about where to place computation, but it also automatically places computation based on what it observes in the graph. We built this so that it can actually move from running sort of inference models, small models on the phone, to single machine training, and then doing large-scale training in data centers or deployment. And you want to be able to take the same kind of description of your model and use that in all these different places. Okay, so you should check out TensorFlow if you are interested and think it might be useful for your problems. So I think the main conclusion is that computers have made pretty big strides in a lot of different kinds of tasks in the last 5 years in things like speech recognition, computer vision, and language understanding. There have been pretty big advances. And really, these kinds of problems, I think, are really amenable to neural nets, and there's been a lot of progress in those areas. You should certainly look at the kinds of problems you're working on and say, I wonder how I could use neural nets in the problems I'm working on. I think it would be pretty useful. And we released TensorFlow to collaborate with the community in building sort of what we think of as a pretty good machine learning platform, and we hope people will contribute or use it. And there's more information you can find there, and I'm happy to answer questions. In fact, I think the questions, you've already asked questions and queued them up here, conveniently.
Thank you. First of all, why don't we applaud him for...
Thank you. Thank you all for coming.
So, and then we have a collection of questions that covers both AI or machine learning and also generic engineering questions. So I'm happy to introduce our moderator for question, who is Kyungmin who is a software engineer at Google. Welcome.
Okay. Thank you.
What do you think is the biggest difference between machine intelligence and human intelligence?
I mean, I think computers have made advances in the last few years, but we're nowhere near building human intelligence. I think the main thing that human intelligence really is so much better than computers at is just understanding the world by observing and being able to apply the information that you get from those observations to new and diverse kind of situations. I can solve any sort of task with my hands. Well, not any sort, but like if I want to pick up something and it's not something I've never seen before, I can take information about how to pick that up by just building on the wealth of knowledge I built up throughout my lifetime and doing that. And same thing with kind of understanding higher level language and so on. I think computers are not quite there yet. But we're working on it, which is good.
And we are looking forward to AlphaGo's match against Sedorly. So who do you think will win the game?
Yes. Everyone's very excited about the AlphaGo match. I think it's going to be very, very interesting and exciting. I'm not sure. I think the fact that the AlphaGo was able to beat the European champion 5 or 6 months ago is pretty interesting and impressive, but he's quite far away from the strongest player in the world. So on the other hand, it's had 5 more months to learn and to play itself. And one of the advantages of the system is that it learns by experience and it plays itself in order to improve itself. So the question will be, is 5 more months of training enough? Or does Lee Sedol still have the computer's number? I think, I don't know. I will not place any bets. I think the computers have a good chance, but it's not assured.
Next question. There are so many open source libraries for machine learning, such as CNTK and Caffe. So what are the distinguishing advantages of the TensorFlow?
Sure. Yeah, there are certainly quite a few different open source packages. Some that aren't mentioned are Theano and Torch as well. And I think all of them have different strengths and weaknesses. I think we actually took some of the nice features that we liked about some of those other packages and used them as kind of design principles for our system. So we, for example, have automatic differentiation in our system, like Theano has. We had some people from the Theano development group in our group, and they really advocated for that. I think one of the strengths of TensorFlow is it's both pretty flexible from a research standpoint, but it's also pretty good at going from research idea all the way into deploying that on a production system, be that in a data center or in mobile apps. So we've got a fair number of systems at Google that deploy TensorFlow models in their Android apps, for example, and that I think, and being flexible and using the same system all the way through is something we see as a pretty big distinguishing characteristic.
And I wonder what made you the distinguished engineer. So to grow as a great engineer like you, what can I do every day?
Eat breakfast. No, I don't know. I feel like one of the things I like doing is moving around from area to area from time to time and finding a project that I can work on where, the people on the project have different areas of expertise than I have. I feel like when you bring 3 or 4, 6 people together and they all have different areas of expertise, you collectively kind of do something that none of you could do on your own because you don't have all those areas of expertise. And in doing that, you often learn a lot about the other person's area that they know a lot about. And that, I think, is a really good thing, because then you might go off and do some other project, and now, in addition to being able to do this thing, now you know a little bit about this other thing, and that will probably serve you well on the next thing you do. So.
Oh, this is a long question. Yeah. So obtaining data in quality and quantity is not easy for small-sized startup companies and laboratories of a university, while a large company like Google can collect a large amount of data. So could you advise for small entities that are working on machine learning? So, and small-sized companies can afford the large computing power. So could you advise for that perspective as well?
Sure. So, I mean, I do think, there are some advantages large companies have in terms of access to, large numbers of users of your products and so on. But on the other hand, I think one of the things we've found is that things like transfer learning, where you take a problem where there is a public data set available, and then you want to make a model for your particular problem, which is similar but not exactly the same. For those kinds of things, you can actually start with a model that works well trained on the public data set, and those are often generally available. You can download them from lots of places. And then you can do a bit of training on sort of data that is more customized to your particular problem. So you might only need, a handful of examples, or 1,000 examples or 10,000 examples that are labeled for your particular problem when you start with a data set that is similar and is available. And
I have a question. Do you guys have a plan to open your data set on public?
So certain kinds of data we can't release for data related to user behavior we generally don't release except in very aggregated forms, but for other kinds of data we may be able to do some of that. I don't have anything to announce now, but I think the lesson of ImageNet, the ImageNet data set that was released and put together by Stanford, I think has really pushed computer vision forward a lot, and I think everyone recognizes that lesson and believes that if we put out other kinds of interesting data sets, that might actually be a pretty interesting thing to do.
How about the other data set, like speeches and things like that?
No plans at the moment, I can announce. And about affording large computing power, I think one of the actual benefits of being able to use cloud service providers is that allows you, when you sometimes need a lot of computing power, you can use it and get it on demand. So I think that's actually a really big benefit these days, that you can depend on those kinds of systems for occasional uses. Now, if you find that you're using a lot of computing power all the time, it's probably more cost effective in some cases to have some of the machines yourself. But I think you can do large experiments for a week or two at a time pretty readily using existing cloud providers.
And what was the biggest mistake in your life as an engineer, and how did you deal with that?
Oh, there are so many. All right, I will relay a tale. So, does everyone know what Bigtable is? So Bigtable is this large structured storage system that we put together in like mid 2004 and 5, and that system did not have distributed transactions. So if you wanted to update data spread across more than one row of this kind of large table, you had to kind of roll your own transaction protocol. And we didn't put that in because it would have complicated the system design a fair amount. But in retrospect, lots of teams wanted that capability. And so they ended up rolling their own transaction protocol on top of Bigtable. And sometimes they would do it correctly. Sometimes it wasn't quite correct. And really, that was something that we probably should have provided in that core system. We actually could have used it internally in the implementation a few times as well. So we didn't have that. We built a follow-on system called Spanner, and we added that. So I guess people have found that useful to have that capability built into the storage system is the lesson.
Yep. If one is developing an AI that plays a game, does he or she need to be an expert on that game? And how good AlphaGo researchers are at playing Go game?
I'm going to generalize the question a little bit to if you're trying to use machine learning to solve a particular problem, do you need to be an expert in that domain? I think in some cases that's pretty helpful to have at least someone involved in your project that has some domain expertise to understand if the model is doing something sensible or not. But in a lot of cases, I don't think most of the people involved in this need to necessarily understand this. So for example, if you're working on medical imaging, I think it's very helpful to have a radiologist to help you interpret, is the model giving good answers for x-rays? But not everyone needs to understand what is in the x-rays. In terms of AlphaGo, I know that at least a couple of people involved are actually quite good Go players, but there are many people involved who are more developers or machine learning researchers and don't necessarily play Go very strongly. Although I guess they could learn pretty well by playing AlphaGo.
And I believe you've faced many problems and solved them while working on projects. How do you solve those? Do you search on Google when you have a question? Or do you ask your colleagues? I wonder how a guru like you approaches problems.
I do all of the above, I guess. I don't know. I mean, I think, search engines are useful. So I do use search engines. Often having a discussion with a colleague is actually a really useful way. Well, it's one of the things I really like about working at Google is we have people with, all kinds of backgrounds and expertise, and you can often find someone who's an expert in, high temperature ceramics or something. If you need to go find someone with that expertise, you can. So that's really helpful. Often you can have good conversations with people and understand and learn a lot by consulting the right people. I think one of the things about there are some people that have this incredibly broad and wide sets of knowledge, and you sometimes kind of learn who those people are when you're working with them, and you learn you can go ask this person about almost anything, and they'll be like, "Oh yeah, I used to study that," or whatever. So.
In addition to well-known applications of deep learning, such as vision and speech and languages, what are the next applications of deep learning by Google? And when you find an application of deep learning, how do you evaluate the applicability of deep learning?
Let's see. I mean, I think the areas of robotics and healthcare, more generally than just Google products, I think those are going to be pretty interesting domains for the use of machine learning and machine learning kinds of models, because there are interesting data sets in the case of healthcare, and I think the computer machine learning techniques are starting to work well enough that they're going to be pretty applicable to some kinds of healthcare problems. And I think robotics is going to be pretty changed in the next few years, because if you remember the computer vision slide and how much improvement we've got on ImageNet, essentially computers have gone from not being able to see all that well to being able to see pretty well. And that's going to be useful for robotics, right? If you're trying to build robots, if it's helpful to be able to see. So in terms of evaluating the applicability of machine learning, I think it's important to understand, is this similar to another problem that's been already solved or worked on with deep learning, and then what can you learn from that? Are there interesting data sets available for this particular problem is another thing to look at. Do we, just intuitively feel this is a problem that should be solvable by the kinds of models that deep learning kind of can do? I think those are the kinds of things you weigh in your mind when you say, oh, should we tackle problem X with deep learning?
Yes.
I don't know. If they're facts, they must be factual, I guess. Otherwise, they're not facts. I don't know. The whole Jeff Dean facts thing is a bit of it was an April Fool's joke by some of my colleagues that has kind of gone awry. They set up a complicated server internally and people could submit new ones and vote on them, and like I don't know. It's very flattering but embarrassing. So.
Yep. When a trained program fails, it's hard to pinpoint the codes and fix them. So if parameters are manually tuned, it's hard to expect changes in the performance. So how do you tune while avoiding side effects and unexpected changes?
Right. So this is kind of the general complaint against neural nets is that they're somewhat opaque. You know, you feed in data and it gives you some output, but there's not a lot of understandability about why it produced that particular output, particularly if the model is very deep and complicated. This is actually one of the hesitations our search team had about releasing neural nets for search ranking, is when the system made a mistake, they wanted to be able to understand, you know, why is it doing that? And in general, you don't go in and like manually tweak the parameters. What you try to do is understand why the model is making that kind of prediction, and then figure out, is this something from the training data? Is the training data kind of mismatched to my particular problem? Sometimes that happens. You train on one distribution of data, and then you apply it in a case where maybe the distribution of data is not exactly like that. So search is actually a good example. The distribution of queries you get every day changes a little bit, right? Because tomorrow we might get a few more queries about the New York Chocolate Festival or something than we did today, because it's that time of year or whatever. And it's important to understand, is your problem one where the distribution is very stable, like speech recognition, the sounds people make don't change very much from day to day. But for queries or, you know, document contents that are changing quickly, like news, it's pretty important to make sure your model is fresh. And also, I think, more generally, we need to do a better job of building tools that allow us to understand what's going on inside these neural nets, what kind of is causing this prediction to happen. In some sense, this is what neuroscientists are trying to do as well, right? They're trying to understand what's going on inside real brains. We have the advantage that this is software, though, so you can actually measure stuff very carefully and look at every individual value in this system and sort of instrument it however you want. So I think that's a nice advantage.
So the Google has nice tool to reason about, debug about the model itself. Interesting, actually, like if you're using TensorFlow, so if there's a nice tool, then you can actually visualize or
So we've built some tools, and you know, some of them we are released as part of TensorFlow. We have some that are sort of more particular to a particular kind of model or application area that are not associated with TensorFlow. They're just something that team built. But in general, I think visualization and an understanding are an important thing that we'll be working on, and some of that will make its way into TensorFlow. But yeah, I think it's something the whole community needs to work on, is better interpretability and understandability.
And what is your favorite programming language and why?
I have a bit of a love-hate relationship with C++. I guess it's pretty good for some kinds of things, but it's gotten very complicated over the years. Like every C++ 11 or 14 or whatever we're on now adds a whole bunch of new features, and they're all kind of complicated. Most of my work day to day is in C++, but I kind of have never programmed very much in Go, but I kind of like Go that some of my colleagues developed. It seems like a nice, clean, simple language for pretty good for fairly low-level things. The best language I ever worked on was actually one I worked on in my PhD work called Cecil. which was a high-level object-oriented language, and we actually wrote a whole compiler for Cecil in Cecil, which was nice.
All right. So this is actually the last slide. So let me ask you one last question while our YouTube team is preparing to shut down the live one. So we are here in Campus Seoul, where the Korea's lots of startup scene is happening here. So would you be able to provide some guidance or advice for those small-sized startups who are interested and who needs to improve their technical excellency, not as an individual, but as a team or as a company level?
I don't know, maybe. I think when you're a small team, like picking new teammates is a really important aspect of building sort of a company or a project successfully, because you want to find people that have both the right kind of technical skills, but also that are fun people to work with, that you trust and can rely on, that kind of have a diverse set of interests and backgrounds in all manner of things. I think that's going to serve you well. I like to find people who are very broad in their knowledge, because I feel like they're incredibly flexible. They can, work on low-level optimization of GPU cards one day, and then if what is important for the company tomorrow is to go learn about how to do, computer vision models or something, that's something they can do. And having that flexibility is pretty important as a small company. So I don't know. And have fun. Build cool stuff.
Thank you.